Familiar devices which measure and indicate degrees of temperature, inches of length, or minutes of time can be called instruments. These two films will examine instruments used in power plants to measure and indicate such important factors in the system operation as steam, air, and oil pressure, a variety of temperatures, rates of flow, water and fuel levels, and of course changes in operation of equipment and controls. Special analyzing instruments also keep watch on chemical processes, such as combustion and boiler water composition. Let's do some review from an earlier lesson. First, we mentioned that a force per unit area was called pressure. Usually, the unit of measurement is in pounds per square inch gauge, abbreviated PSIG. Now that means pressure in addition to local atmospheric pressure, about 14.7 pounds per square inch at sea level. And if we measure in absolute pressure, PSIA, we're measuring from 0 atmospheric pressure. The same pressure read on a standard gauge, PSIG, will read lower by 14.7 pounds than if read on an absolute scale, PSIA. A compound gauge would read above or below the 0 point of atmospheric pressure. A vacuum gauge reads only pressure below atmospheric 0. Some gauges may not indicate at all until a certain pressure has been reached. We call this a suspended range instrument. To measure the weight or pressure of atmosphere, we use a device called a barometer. At sea level, this normally will be about 14.7 pounds per square inch. If we seal a long glass tube, fill it with water, then invert it and put the opening into water at sea level, the pressure of the atmosphere will hold water up in the tube. This column will be almost 34 feet high. As barometric or atmospheric pressure changes, height of the water column will rise or fall also, always equaling the pressure on the water at the base. Well, let's use, instead of water, a very heavy liquid, mercury. The same sea level pressure will only raise mercury about 29.92 inches, because mercury instruments and predictions are based largely on barometric changes or pressure patterns across our country in inches of mercury. Liquids in a tube will have a curved top. When measuring or reading a column height, always read the center of the column, not the edges. If atmospheric pressure drops, height of the mercury column will also fall. Extra mercury raises the level of the well. The measurement must always be made from the top of the well level to the column top. A manometer is like the barometer tube, except it measures air or gas pressures. The tube is open to atmospheric pressure, and any rise in the column must be caused by pressure acting on the well surface. This type of instrument is called a single leg or a well gauge manometer. We reverse this to make a vacuum manometer, also measured in inches of mercury, usually. As less and less pressure is exerted on the top of the column, the atmospheric pressure on the well forces the mercury up the tube. Some manometers have inclined tubes, so the scale can be more easily read. These are called, quite appropriately, inclined manometers. One frequently used instrument is the U-tube manometer. Here, two pressures can be compared. The usual measurement, again, is inches of water or mercury. Instead of manometer tubes, a compact instrument can be made using a flexible membrane or metal diaphragm on one side of a sealed chamber. Even a very slight change in air pressure will cause movement of the diaphragm. Connect this to a pointer and the unit will indicate changes in pressure. A calibration spring acts to return the pointer to 0 when pressure is removed. If we desire to measure the difference in two system pressures, we can seal off both sides of the diaphragm and make the gauge respond to this difference. When pressures are equal, the pointer indicates 0. If you've ever been to a party with a paper roller type noisemaker, you know that applying air pressure unrolls these snakes and makes them flap and wiggle. They roll up again as you release the air. So it is with any bent tube under pressure, even your own garden hose. The popular board-on tube is a sealed metal device with a curve in it. Pressure causes the curve to open somewhat. It really does not move much. A pivot and amplifying linkage is made part of the gauge so the scale can be larger and more easily read. Manometers, bellows, gauges, or board-on tube instruments all read pressure where it's measured, sometimes quite a distance from the operator. So, we use devices which are able to convert electric voltage or pressurized air to a signal based on its own reading. This signal voltage or pressure is transmitted by wires or small tubes. At control or instrument stations, these transmitted signals are displayed for the operator. These same signals may also be used to operate other control devices which hold pressures within proper ranges. Instrument air, usually at 30 psig, is provided throughout the plant. The transducer on this pressure steam line reacts in such a way that it keeps 24 psig in the instrument line. As pressure falls, the low pressure or signal reduces in proportion. If the main pressure goes up, the signal will also go up. Electric transmitters are often some type of variable resistor controlled by the pressure of the gauge. As the pressure changes, so does the voltage passing through the resistance. Now, if we want to transmit pressure readings through the plant, we'll also want to do the same with temperature. Temperature instruments are somewhat simpler. Most are electrical devices. A pneumatic, that is, air-operated transducer, which reacts to temperatures, provides a low-pressure air signal, which varies with changes in the main temperature. A simple electrical signal device, the thermocouple, works on the principle that when two different metal wires are joined and this junction is heated, a very small voltage will be produced. The heat difference of the heated junction and the cooler end of the wires can be read by a sensitive millivoltmeter. Since the electrical resistance, measured in ohms, of most metals increases with temperature, a resistance thermometer can be designed. Instead of just an ohmmeter, this type of instrument uses a Wheatstone bridge to read changes with great accuracy. Here, known and calibrated resistance is used to balance exactly the heated resistance to be measured. This then is referred to a temperature chart or automatic balancing devices which give readings of remote temperature without consulting conversion charts. Often a recorder. Some recorders use a continuous roll of chart paper slowly moving past the marker. Many units can record 2, 3, or more signals on one chart. Now the operator can quickly compare several temperature and pressure readings to see how the system is trending. It is very helpful to know not only the readings now, but also what has been happening. Many semi-mechanical transmitting devices to measure temperature or pressure are being replaced by small solid-state electronic devices coupled with transistorized amplifiers. And what about flow measurement? We can't conveniently measure actual volume of flow per minute like our friend seems to be doing here. Instead, many power plant flow instruments use a device called an orifice plate, a disc with a hole slightly smaller than the inside of the pipe itself. Connecting a U-tube manometer filled with mercury will show us that there is more pressure on one side of the orifice plate than on the leaving side, and this difference increases as flow increases. Adding a float, pointer, and scale, we have an instrument which changes as changes in flow create pressure differences across the orifice. Diaphragm-type differential gauges may be employed in place of the U-tube manometer. They may also be linked with a transmitter for remote instrumentation. Other devices, such as the rotometer shown here, actually use all or a portion of the flow to raise or lower a ball or plug inside a glass tube. Again, the faster the flow, the higher the indicator is pushed. Other flow meters, like the water meter in our home, use fluid flow to rotate a wheel or plate, which is connected to a geared meter or to a transmitting device. Both flow speed and actual volume can be indicated. But what about water level in a pressurized system? Floats are not practical in many cases. Instead, we take advantage of some physics, which says that water bends light rays slightly. Now, this fellow thinks the fish is several inches to the right of its true location because the beams of light are bent when they leave the water. The bicolor gauge glass uses this principle. The light is bent down by the water, so only green color is seen when water is in the glass. But only red is seen if the level of water is below that slight point, as shown here. See the red or green color. Others use television cameras to monitor water levels, especially in boiler drums. Other installations use the weight of water to indicate the level inside. The fuller the vessel, the more weight or pressure at the bottom. A diaphragm-type differential pressure gauge measures the pressure above the water with the pressure at the bottom, which includes the weight of the water. The gauge is calibrated to show water level or percent of fill. Some instruments are built with adjustable alarm contacts, which signal when the pointer hits them. Others have electric or pneumatic transmitters to control rooms or other supervisory panels. Okay, it's time now for a little quiz. Turn to page 28 in your booklet and take the quiz for cartridge number 1. Restart the machine when you complete the first 10 questions and we'll go over the answers with you. The answer to number 1 is false. Pressure can be measured in inches of mercury or water, pounds per square inch gauge, PSI-A, or several other ways. 2 is also false. A gauge which measures above and below atmospheric pressure is a compound gauge, not a suspended range gauge. Number 3 is true. The correct way to read a liquid manometer is to observe the center of the column, not the edge levels. It is also true that a diaphragm-type gauge can be made very sensitive to even small changes in pressure. True for number 4. For large pressure ranges, the Bourdon tube gauge is often used, and like the manometer and diaphragm gauge, this instrument measures pressure, not temperature. So number 5 is false. And so is number 6. Instruments usually transmit a signal by air pressure, called pneumatic systems, or by electricity, not by hydraulic pressures. Number 7 is true. The orifice plate acts as a resistance to flow. The greater the flow, the greater will be the difference in pressure. Number 8, false. The change in a bicolor gauge is the result of water, not steam, bending the light rays. Another way to check water level is by measuring the weight or pressure differential of the water. So true is the answer to number 9. Or more conditions over a period of time. Okay, in the next film we'll look at instruments which analyze what's happening in our boiler and turbine as part 2 of instrumentation systems. When the machine stops next time, you can either review this cartridge again or go on to part 2 of instrumentation.